Welcome to this explainer. Let's just dive right into things, shall we? Today, we're going to completely deconstruct what is arguably the most famous poster in the entire history of science, the periodic table of elements. We have all seen it hanging on the wall of a high school chemistry lab. You know the one, that perfectly neat, color-coded grid that seems to organize all the building blocks of the universe into one master chart. It looks entirely complete, doesn't it? Like this giant puzzle where every single piece has finally been snapped right into its rightful place. But today, we're going to look at some truly fascinating evidence that shows us exactly why this comforting picture is actually hiding a much more chaotic and, frankly, far more interesting reality.
So the crucial point we really need to start with is this question right here. Is the periodic table actually finished? The idea that it's this closed, completed map of matter with absolutely nothing left to say about it is a massively widespread assumption. It's incredibly easy to just believe that chemistry simply ran out of new ideas or new elements to discover, and that the book on fundamental matter is shut for good. But what if I told you that the chart you memorized back in school is actually just a single, fragile chapter in a much, much larger story?
Take a look at this massive breakthrough from 2026. Physicists at the Institute of High Energy Physics in Beijing announced the strongest evidence yet for something called a glueball. Now, if you haven't heard of it, a glueball is a particle predicted to be made almost entirely of the glue that holds quarks together, meaning it contains little to no quarks of its own. This is a huge breakthrough, and it completely shatters the illusion of a finished table of matter. The hunt for the glueball proves that physics is still finding totally new, fundamental, basic states of matter right now. It forces us to ask, shouldn't there be a more general table spanning all of matter, one that our chemical periodic table just sort of fits inside of?
All right, let's move into Section 1, the chain of matter, building the universe step by step.
To really wrap our heads around this, we've kind of got to reframe how the universe is actually built. We need to stop looking at atoms as the ultimate foundation and instead see them as just one single layer in a massive physical hierarchy. The universe builds itself step by step, and atoms, well, they're really just sitting right in the middle of that construction project. Let's start from the very bottom and walk through this chain. Step 1. Quarks and gluons bind together through the strong interaction to form hadrons. These are things like protons, neutrons, and, yep, exotic states like that glue ball we just talked about. Step 2. Protons and neutrons bind together through the residual strong interaction to form atomic nuclei, or isotopes. Step 3. Those nuclei use the electromagnetic force to bind electrons, forming atoms. And finally, steps 4 and 5, atoms combine through chemical bonds into the molecules that make up you and me. What you absolutely need to take away from this is that at every single step, a completely new bound state is formed from the structures before it. And crucially, at each step, totally different physical principles take over and set entirely new rules for how those blocks can combine.
Now, what's just absolutely wild here is what happens down at that very bottom layer. According to quantum chromodynamics, or QCD for short, there's actually no known upper limit to how many hadrons can exist. The theory of the strong interaction just keeps allowing new binding configurations. We're talking more quark pairs, higher excited states, and as our experiments get more and more sensitive, physicists just keep finding them one by one. The family of matter at this fundamental level is ever growing, literally with no end in sight.
And you know, this brings us to a massive contradiction. Just think about this quote from our source material for a second. The periodic table is just one link in that chain, the atoms layer, sitting between nuclei and molecules. If the hadron layer beneath it has absolutely no limit, why does the atom layer, our beloved periodic table, look so perfectly finite and orderly? Why does chemistry seem to have a hard stop while fundamental physics just keeps on going?
Which brings us to Section 2, hitting the physical walls, the boundaries of nature.
We're about to realize that the table's so-called finiteness doesn't actually have anything to do with chemistry, just running out of combinations. Instead, chemistry is effectively trapped inside a room built by fundamental physics. Take the number 118. This is the total number of elements currently sitting on the periodic table. It's the absolute limit of the finite table that every chemistry student memorizes. 118 elements in total, it acts as our expected, comfortable boundary. But researchers? They aren't stopping there.
Because right now, literally as we speak, researchers are actively hunting for element 119. But here's the catch. Pushing the boundary this far takes us completely out of the realm of standard chemistry. When you try to create element 119, you are hitting the absolute limits of nature. It becomes a fundamental physics problem, not a chemistry problem. Why? Well, because as you keep adding protons to a nucleus to make bigger elements, the electric charge of that nucleus grows incredibly strong.
And man, if we look even further down the theoretical road, we hit this terrifyingly fascinating wall right around atomic number 173. At element 173, the electric charge of the nucleus is so overwhelmingly powerful that the innermost electron has to orbit closer and move at unimaginably high speeds just to stay bound to it. Theoretical calculations show its binding energy would actually need to exceed twice its rest energy. And when that happens, the vacuum itself becomes unstable. The very fabric of empty space around the nucleus would start spontaneously producing electron-positron pairs. Past element 173, the ordinary textbook concept of an atom simply stops holding up. The physics literally just breaks down.
So the real takeaway here is that we're essentially boxed in by two completely independent physical walls arriving at roughly the exact same place. First, you have those relativistic limits on electrons, causing the vacuum instability that we just talked about. But honestly, long before you even reach that, you hit the second wall, nuclear instability. Protons naturally repel each other, right? In super-heavy nuclei, they repel each other so strongly that even if you can somehow assemble them, they blow themselves apart in a tiny, tiny fraction of a second. The finiteness of the periodic table isn't some beautiful design principle of chemistry. It's a strict boundary that nature imposed from the outside.
Let's move on to section 3, the messy middle, where chemistry breaks its own rules.
But you don't actually need to look at those extreme super heavy elements way out at the edge of the table to see its orderly design start to crack. We can pull back from those theoretical extremes and look right at the very center of the poster hanging on your wall to expose the internal chaos. I'm talking about the transition metals. Stretching all the way from scandium to mercury, this giant block right in the center is by far the most complicated part of the periodic table. Across the rest of the table, electrons fill their shells in a largely smooth, predictable order. Every new element adds one electron to the outermost shell, and their chemical properties change with this beautiful regularity. But the transition metals? Oh, they completely break that pattern. Let's just look specifically at chromium to see exactly how weird this gets. Based on the simple filling rules you learn in standard chemistry, chromium's expected electron configuration should be argon 3d4, 4s2. But its actual configuration in reality, it's argon 3d5, 4s1. The electrons completely unexpectedly start filling the inner d subshell, while the outer s subshell is just abandoned halfway. It flips the textbook configuration entirely on its head, leaving that outer shell hanging halfway empty.
And hey, chromium isn't just some one-off fluke either. Copper does the exact same thing. We expect it to be argon 3d9, 4s2, but nature decides it actually wants to be argon 3d10, 4s1. This isn't just a handful of random exceptions. This is literally the defining feature of the transition metals. They simply do not behave as a single, orderly family the way the alkali metals or the halogens do.
So why do these simple rules fail so miserably here? Well, it's because the energy gap between these subshells is incredibly small, which allows a chaotic mix of forces to just take over. You've got exchange energy, electron correlation, which is basically electrons shifting around to avoid each other's repulsive forces to find the absolute comfiest arrangement, and even relativistic effects. They're all working together to produce electron arrangements that just happen to be more stable than the simple textbook prediction. There is no single rule behind this. It is a complex battle of multiple physics forces, which is exactly why chemistry students just have to bite the bullet and memorize a huge chunk of these configurations by heart. And honestly, the chaos only deepens as you move further down the table. When you add f orbitals to the crowd down in the lanthanides and actinides, the simple filling rules completely collapse against the intense many-electron physics of this region. That neat little poster on the wall really does an amazing job of hiding all of this intense, messy physics, doesn't it?
Let's wrap things up with Section 4, a new perspective, chemistry as an open puzzle piece.
Okay, it is time to bring all of these concepts together and really shift our mindset here. We need to stop seeing chemistry as a closed system. Here is what you should really take away from this explainer. First, the periodic table is a tenant. It's renting space inside a much larger physical framework dictated by relativity and nuclear physics. Second, chemistry doesn't exist in a vacuum. It studies just a very narrow middle slice of matter's massive organizational chain. And finally, those ongoing discoveries in physics, like the glue ball we discussed, are a powerful reminder that the links of the chain directly below atoms are still actively being discovered today. The universe's chain of matter is far, far grander than one single chart.
Which leaves us with one final, pretty provocative thought to ponder. If we stop treating chemistry as an isolated absolute law, and instead treat it as just one fragile, messy, and beautiful middle link in a much longer chain of bound states stretching from quarks all the way to molecules, do the periodic table's seemingly unsolved features start to look a little different? Perhaps the chaos of the transition metals and the invisible walls bounding the super-heavy elements aren't actually flaws in the table at all. Perhaps they're the exact places where the table is trying to connect to the rest of the universe. Thank you so much for joining me on this explainer, and always keep questioning what you see on the surface.